So to get us going, the very first thing we started talking about was what a limit looked like if we took a look at the picture, as well as if we took a look at the values in a table. So I'm going to take a look at this function right here in my graphing calculator, 3 to the x minus 2 to the x over x. It's something that if we tried to evaluate it here at 0, we wouldn't find a value. But if you think about what's the actual limit going to be, that's 3 to the 0. Oy. 3 to the 0 minus 2 to the 0 over 0. So 1 minus 1. So this is that situation which we had talked about is more interesting than just saying it does not exist. Any constant divided by 0 still doesn't exist. But a 0 over 0 situation is one where we have to apply some of our calculus techniques to figure out if that limit does in fact exist. So let's take a look at the picture and see if we can use it to come up with some idea of what the limit is doing. So I'm going to put in 3 to the x minus 2 to the x and divide it all by x. We'll just have the default window. We can change it once we have a look. We'll see what this picture looks like. And I'm interested at x equals 0, which on my screen it's in there. But you'll notice it's fairly hard to see right now. So let's zoom in around this area right here. I'll change this window. Let's go from -2 to 2. And I can probably go from 0 to 4. So if I use that picture, the TI-83 will still tell you there's no value at 0. If you try and evaluate it at 0, it'll say it's undefined. But I'm not sure how you've gotten used to doing this. One easy way to do it is this trace button. If you hit the trace, then you can move along, trying to figure out if I move to x equals 0, what'll I get? So see, my TI-83 is still saying I don't know what it is when x is equal to 0. But if I'm very close, it's about 0.4 and a little more than 0.4. If you want better resolution, you have to zoom in more. So what I mean is, if you want to know what's closer, we'll have to make this window, try it -0.5. And we'll try 0.5. That way I get a closer look at it. And when I trace, the values will be closer together when I trace. Okay. So it looks like, geez, it's really close to 0.4016 something there. Okay. So let's, I think that's what I'm going to call it here, is I think it's going to be 0.405, something like that. So based on our graph here, my picture would look like this. It looks like it's about 0.4, we'll call it 0.5 from my picture using that trace button. And then of course the other way to do it is with a table of values. So one thing you got to make sure is the TI-83 has some functions for working in tables, and before you go to the table you should make sure they're turned off. So I go to table set, second function table set, and you see here how this stuff is on auto. That's some of that we're going to turn off. So I'm just going to say I would like the independent variable to be something you ask me for, not something you try to fill in automatically for me, but it'll calculate the dependent automatically. So now when I go to my table, it's waiting for me, and I'll try values near 0. So for example, 0.01, 0.001. So it's getting close to 0.045, just like we had found when we were looking at our graph. You can also approach from the other side, which would look like this. Oh, sorry, that's -1. A little sleepy this morning. So from the left and right side, all those values are still getting very close here to 0.045. So I'll just put a couple in my table. So I had 0.01 and 0.409. And I don't know why this pen is so clingy this morning, but 0.001. So this was fairly time consuming. That's why we want to go with some algebraic methods, and it's not even exact. We will have techniques to tell us how to do this exactly. We could find this one, but for now that's the basic approach we started with, and it is still one which you can use to help confirm your work. If you're doing it algebraically and you're not sure if you're correct, you can fall back to using the graph or a table to do that limit as well. But we should eventually have some techniques to do it. This one here we can't substitute directly because when x equals 3, this bottom here is going to equal to 0, and I can't divide by 0. So does anybody have a suggestion for a technique that would help me remove this problem? Factor? Yeah, so we can start. One thing we can do, we're going to need to do more than just factoring here. Yeah, so this is one of my factors, 3 minus x, 3 plus x. And this was that rationalizing the denominator you would have done in probably grade 10 or 11, where you had to multiply by a conjugate. So I don't want to work with these radicals here. What I'm going to do is I'm going to multiply the top and bottom by root 2x plus 3 plus 3. And the same on the bottom then, so that it's still equal. 2x plus 3 plus 3. And that's a difference of squares pattern. So now I have the limit as x goes to 3 of 2x plus 3. And I'm going to take away 9. On the bottom, I still have 3 minus x, 3 plus x, and root 2x plus 3 plus 3. So if I start to collect up like terms now, I'm going to have the limit as x goes to 3 of 2x minus 6 over 3 minus x and 3 plus x. So at this point, I can factor this so I can get rid of the problem, and I'll show you the factoring that I'm going to do. I'm going to take out this 2. And, oh, it's so close. It's so close. It's x minus 3, not 3 minus x. Good. And if I factor out a negative, I'll be able to reverse it. Now, just in case you're on autopilot and you're losing sight of what we're doing and why we're doing it, this is what's causing the problem here. Because if x equals 3, that divides by 0. That's why I'm trying to factor it or divide it out or remove it. Because if that's gone, there's no more problem with x equals 3. So this will be now the limit as x goes to 3 of negative 2, 3 minus x, 3 minus x, 3 plus x, and that radical that we had from the top. So these are out, and I've removed my discontinuity, the problem where the limit didn't exist. And now I have something I can substitute directly. Negative 2 over 3 plus x root 2x plus 3 plus 3. So if I substitute in directly, I'll find this limit. It's going to be 6 times, let's see here, root 9 plus 3. Yeah. So negative 2 over 36, which we could also call negative 1 over 18. So just to give you an idea, this was meant as an entire lesson review. This was not meant as a, hey, let's warm up into this. This is, if you know how to do this, this pretty much practices a lot of techniques we talked about with finding limits algebraically. It uses factoring, it uses radicals, it uses simplifying and factoring things out. So if you're comfortable with this example, you can safely probably assume that you're on the right track with the lesson on evaluating limits analytically. Okay, we'll talk a little bit more together about some simpler practice, but that basically represents all the tasks you'd have to do from that unit. Okay, so the intermediate value theorem. I don't know why, sometimes I'm always curious how a theorem gets picked. This is one of those theorems that's kind of like, oh, shouldn't this just be called the duh theorem? Like, if a graph is continuous and you go from one point to the next, you have to go through every point on the way. That's what we said when we said continuity means you don't pick up your finger when you trace the graph. You have to go through every intermediate value on a continuous graph. So sometimes when we're doing, there's a lot of math where mathematicians, all they want to do is know if the answer exists. Sometimes that's the question they're trying to answer. They don't want to find the answer because that might be so hard that it's not worth investing your time yet. First they want to know, does this problem have an answer before I go looking for it? So that's one of the reasons intermediate value theorem is used, is does this have a solution? This equation, x to the 4th plus 1 equals 1 over x. If I want to tell you that, yes, I found an area that has a solution, I can use intermediate value theorem to do it. And the way I can make that happen, I'm going to write this as x to the 4 plus 1 minus 1 over x to be equal to 0. And I'm going to call this f of x. Just make it easier for us to talk about it. So in my margin, if I'm being a good mathematician, I'd probably write f of x equals 0 is equivalent to this having a root. So if I look, what happens at f of 1/2? And being a good mathematician, I'm ridiculously lazy with this kind of stuff, so I'm going to use my calculator. And if you don't already do this, I'll review with you a little bit. I'm going to put the function in. So you're probably going to want to practice this because it's something we do a lot. One really good thing about AP is when they ask you to use your calculator, it's really helpful times to use your calculator. It's generally not a tedious thing. And then they tend to save all the tedious stuff where you're like, oh my god, this is so ridiculous. They don't usually make you do that by hand. They usually let you have a calculator to work through that. So there's my function. And what I'm going to do is quit this screen. And then I'm going to use the function, which is under variables here. Y variables. And the function is y1. It's stored back here. See, y1? So then all you got to do is put your brackets around it and then ask what this value is. So negative 0.9375. You can convert that to a fraction if you like. You can hit math, fraction. So negative 15 out of 16. And if I want to find that function at 1, I suppose this one is easy enough to do in your head, but I'll show you again how to use the calculator. You go to the variables button, you go to the y variables, and you choose a function. The function we put in is in y1, and I would like to know what's the value at 1 itself. And that value is 1. Okay. Now, since f is continuous on this interval from 1/2 to 1 by the intermediate value theorem, there must be one value where it's somewhere in the middle so that it equals 0. Why is it? Because it's negative at one spot and positive at the other. The only way you ever get from a negative to a positive is if you go through 0. If that graph's continuous, you had to squish through 0 somewhere. You might have gone through 100 times, but you know that you have to go through at least once. So there is, in fact, an answer somewhere in there that we could go hunting for. Yes, question?
So the main thing with the IUT is that you plug in the x and y's, I mean the 2 points for the restrictions, and then you plug in the type of x, and then you just solve the numbers. And then,
well, what you're trying to show, it's generally that straightforward where you would be looking to use the endpoints of the interval, but basically you're looking to show that one value would be positive and negative, because then if you know you have a positive and you went to a negative, or vice versa, you went from a negative to a positive, that means you had to go through 0. So then you can just quote intermediate value theorem, it has to pass through 0 because it's a continuous graph.
so you're finding if it goes through 0. That's what it is.
I haven't found where it's equal to 0. All I've done is tell you that somewhere it must go through 0. Okay, now I'll just go through a squeeze theorem question with you just so you can kind of have a look at how that works here. Here's a function I didn't give you the value for, so you don't know what this function is, but I'd like you to find the value at -1 if you know this is the case here. So what you can do is squeeze it by going like this. And even though I don't know what's happening to the middle graph, if I'm told that it is being squeezed like this, I will find out what the other limits are. And if I substitute 1 into here, this will be -1 minus -2. And that'll be 1 is less than or equal to the limit as x goes to -1. So the only way that this happens is if it too has a limit of 1. Okay. That's the only possible way that that function could behave. If it's less than or equal to 1 and at the same time greater than or equal to 1, it has to be equal to 1. So for today, that's basically a topic, one question per topic to jog your memory. And then we're going to take some practice from your textbook. We will do another review again next class. But so far, I just want to see where we're at since I was away for a couple of those days in there on our first unit. Okay? So grab your textbooks. We're on page 106 and page 270.